Deep in the constellation of Phoenix, 40 light-years from Earth, a world orbits its star in defiance of everything we thought we knew about planetary formation. LTT 9779b shouldn't be there. Its existence violates the fundamental rules that govern how planets form, survive, and evolve. Yet the James Webb Space Telescope has not only confirmed its presence, it's revealed characteristics so bizarre that astronomers are scrambling to rewrite the textbooks. This isn't just another exoplanet discovery. LTT 9779b exists in what scientists call the hot Neptune desert, a region of space around stars where Neptune-sized planets simply don't survive. The intense radiation from their host stars should strip away their atmospheres in mere millions of years, leaving behind only bare rocky cores. But somehow, impossibly, LTT 9779b has kept its thick gaseous envelope intact. It orbits its star once every 19 hours, enduring temperatures that vaporize metal, yet it persists where physics says it should have vanished long ago. When Webb turned its infrared eyes toward this system, it didn't just photograph an anomaly, it captured data that challenges our entire understanding of planetary atmospheres, cloud formation, and the very mechanics of how worlds can survive in extreme environments. The observations revealed clouds made of vaporized rock and silicate minerals raining down in a permanent storm. They showed an atmosphere so reflective it bounces back 80% of the light that hits it, an albedo higher than fresh snow. And they detected chemical signatures that suggest processes we've never seen on any other world. The discovery forces us to confront uncomfortable questions. If LTT 9779b can exist where it shouldn't, how many other impossible worlds are waiting to be found? What other gaps exist in our understanding of how planetary systems form and evolve? The universe, it seems, is far more creative than our theories allow. The hot Neptune desert and the mystery of missing worlds. The hot Neptune desert represents one of the most puzzling patterns in exoplanet science. When astronomers first began cataloguing planets around other stars using transit methods and radial velocity measurements, they noticed something strange. While they found plenty of massive gas giants hugging close to their stars, the so-called hot Jupiters, and countless smaller rocky planets in tight orbits, there was a conspicuous gap. Neptune-sized planets, those with radii between 3 and 5 times Earth's, were almost entirely absent from orbits closer than about 10 days. This wasn't a detection bias. Telescopes were perfectly capable of spotting such worlds. The desert was real, and it demanded an explanation. Theoretical models quickly provided one. Neptune-sized planets in close orbits experience ferocious stellar radiation that heats their upper atmospheres to thousands of degrees. At these temperatures, hydrogen and helium atoms gain enough kinetic energy to exceed the planet's escape velocity. The atmosphere literally evaporates into space, a process called photoevaporation. Within tens of millions of years, a geological blink of an eye, the thick gaseous envelope disappears, leaving only a dense rocky core behind. The mechanism is straightforward thermodynamics. A star's ultraviolet and X-ray radiation pumps energy into a planet's atmosphere. For smaller worlds without the gravitational muscle of a Jupiter, this heating drives particles to speeds where they overcome gravity's pull. The planet hemorrhages mass, sometimes losing Earth masses worth of material every 100 million years. Eventually, what started as a puffy Neptune ends up as a super-Earth, a dense rocky world with at most a thin residual atmosphere. Observational evidence supports this evolutionary pathway. Astronomers have found numerous super-Earths orbiting where hot Neptunes should be, their sizes and densities consistent with being the stripped cores of once larger planets. They've detected extended atmospheres being blown off planets in real time, measured mass loss rates, and observed the ultraviolet glow of escaping hydrogen forming comet-like tails. The hot Neptune desert exists because these intermediate mass planets can't hold on to their atmospheres in the intense radiation environment close to their stars. Yet, LTT 9779b sits right in the heart of this forbidden zone. With a radius 4.7 times Earth's and a mass 29 times greater, it's definitively Neptune-sized. Its orbit brings it within 0.01, 7 astronomical units of its star, closer than Mercury is to our Sun, completing one scorching lap every 19 hours. The stellar flux it receives is more than 4,000 times what Earth gets from the Sunday. According to every model of atmospheric escape, LTT 9779b should have lost its puffy hydrogen-helium envelope billions of years ago. Instead, it maintains a thick atmosphere that extends thousands of kilometers above the planet's surface. The star LTT 9779 isn't young either. At roughly 2 billion years old, it's had plenty of time to blast away any primordial atmosphere its planet might have retained. The system's age makes the survival of LTT 9779b's atmosphere even more perplexing. This isn't a planet that formed recently and hasn't had time to erode. It's been enduring this radiation bath for 2 billion years longer than it took for complex life to emerge on Earth, and it still hasn't lost its gas. When the planet was first discovered by NASA's Transiting Exoplanet Survey satellite in 2020, astronomers recognized immediately that they had an outlier. Ground-based follow-up observations confirmed the basic parameters and revealed something else remarkable. The planet is extraordinarily reflective. Measurements of light curves showed that LTT 9779b reflects about 80% of the starlight that hits it, making it one of the most reflective objects ever found in the universe. Only the icy moons of Saturn come close in our own solar system. This extreme reflectivity provided the first clue to the planet's survival. Highly reflective worlds absorb less stellar energy, keeping their atmospheres cooler than they would otherwise be. But even accounting for this albedo, the temperatures on LTT 9779b should still exceed 2000 Kelvin hot enough to vaporize rock. Something else had to be protecting the atmosphere, some process or composition that conventional models hadn't anticipated. Early theories suggested the planet might be continuously replenishing its atmosphere through volcanic outgassing, compensating for photoevaporative losses with fresh material from the interior. Others proposed that the planet's high mass gave it just enough gravitational pull to hold onto its envelope despite the stellar bombardment. A few researchers speculated about exotic atmospheric chemistry creating heavier molecules less prone to escape, but none of these explanations fully satisfied the observations. The mass loss rates calculated from the stellar radiation should overwhelm any plausible outgassing mechanism. The planet's gravity, while strong for a Neptune, wasn't exceptional enough to explain the complete retention. The mystery deepened when spectroscopic observations revealed unusual atmospheric features. Traditional Neptune-like atmospheres show strong absorption lines from sodium and potassium, clear signatures of relatively cloud-free gas. LTT 9779b's spectrum was different, heavily muted and featureless in many wavelengths, suggesting something was obscuring the deeper layers. The atmosphere was hiding behind a veil, and astronomers needed a more powerful instrument to peer through it. Enter the James Webb Space Telescope. With its unprecedented infrared sensitivity and spectroscopic capabilities, Webb could dissect the planet's atmosphere in wavelengths inaccessible to ground-based telescopes. When astronomers pointed Webb's near-infrared spectrograph at LTT 9779b during several transits, they captured the most detailed atmospheric spectrum of a hot Neptune ever obtained. The data would not only explain how this impossible planet survives, it would reveal an atmosphere unlike anything in our solar system. Clouds of vaporized rock. When James Webb's instruments analyzed the reflected light from LTT 9779b, they didn't detect water vapor, methane, or ammonia, the usual suspects in Neptune-type atmospheres. Instead, the spectroscopic signatures pointed to something far more exotic. Clouds composed of vaporized silicate minerals floating in the upper atmosphere. This was the smoking gun that explained both the planet's extreme reflectivity and its mysterious survival in the hot Neptune desert. Silicate clouds form under conditions that would seem apocalyptic by terrestrial standards. At temperatures exceeding 1,700 Kelvin, hot enough to melt iron minerals like magnesium silicate and silicon dioxide transition from solid to gas. These vaporized rock particles rise through convection into the upper atmosphere, where temperatures drop slightly. There, the vapor condenses into microscopic particles, forming clouds not of water droplets or ice crystals, but of molten rock droplets and solid mineral grains, suspended in hydrogen and helium. The physics of these clouds is fundamentally different from Earth's water-based weather. Silicate particles are dense, about 3 times heavier than water molecules, and they interact with light in unique ways. Their refractive indices and scattering properties make them exceptionally good at reflecting visible and near-infrared radiation. When billions of these particles form continuous cloud decks across the planet's dayside, they create a mirror-like surface that bounces stellar radiation back into space before it can penetrate to the deeper atmosphere. This reflectivity is LTT 9779b's shield. By preventing most of the star's energy from being absorbed, the clouds keep the atmosphere substantially cooler than it would be otherwise. Webb's measurements indicate that while the planet's dayside would reach over 2,400 Kelvin if it had a clear atmosphere, the silicate cloud deck maintains temperatures around 1,800 to 2,000 Kelvin. Still hellishly hot by any reasonable standard, but cool enough to dramatically slow photoevaporative escape. The difference of several hundred degrees translates to exponentially lower atmospheric loss rates, potentially allowing the planet to retain its envelope for billions of years. The cloud formation mechanism itself is remarkable. Theoretical models suggest that strong winds, driven by the intense temperature difference between the planet's permanent day and night sides, circulate material around the globe. On the scorching day side, silicates vaporize from the hot layers below and rise through convection. As these vapors ascend, they cool and condense into cloud particles. The winds then carry these clouds across the terminator into the night side, where even lower temperatures allow some minerals to rain out as molten droplets or solid grains, falling back toward the surface. This creates a continuous cycle, a hydrological cycle, not of water, but of rock. Webb's spectroscopic observations revealed specific absorption features consistent with minerals like forsterite and enstatite, magnesium-rich silicates, common in rocky mantles and meteorites. The presence of these particular compounds suggests that the atmosphere is sampling material from deep within the planet, possibly from a molten magma ocean layer that exists between the rocky core and the hydrogen-helium envelope. If the upper mantle is partially or completely molten, it would continuously supply vaporized rock to the atmosphere, maintaining the cloud decks over geological time. The cloud particles aren't uniform. Spectral analysis indicates a range of particle sizes, from submicron aerosols, tiny grains smaller than the wavelength of visible light, to larger droplets several microns across. This size distribution affects how the clouds scatter light at different wavelengths, producing the characteristic reflection spectrum Webb observed. Smaller particles scatter blue light more efficiently, while larger droplets reflect across a broader spectrum. The combination creates the brilliant white appearance that makes LTT 9779b shine like a cosmic mirror. But silicates aren't the only exotic compounds floating in this atmosphere. Webb detected subtle signatures of other heavy elements in vapor form, including iron and titanium. At the extreme temperatures on LTT 9779b's dayside, even these refractory metals can exist as gases. Iron vapor, in particular, can form metallic clouds that absorb rather than reflect light, creating darker patches that might explain some of the spectral variations Webb observed. The interplay between reflective silicate clouds and absorbing metal vapors likely creates complex weather patterns with bright zones and dark bands, reminiscent of Jupiter's belts and zones, but powered by entirely different chemistry. The vertical structure of the cloud layers remains uncertain, but models constrained by Webb's data suggest multiple stacked decks. The uppermost layer, where temperatures fall below the condensation point of the most volatile silicates, likely consists of fine aerosol hazes that scatter light efficiently. Below that, denser clouds of larger particles form the main reflective layer, possibly stretching over hundreds of kilometers in altitude. Deeper still, at the base of the cloud decks, temperatures rise again, and particles evaporate back into gas, creating a sharp cloud base, analogous to Earth's cumulus cloud bottoms, except here, the cloud base is where rocks start to boil. The discovery of these silicate clouds has implications beyond explaining LTT 9779b's survival. It suggests a new class of exoplanet atmospheres that we hadn't fully anticipated. Dozens of hot Neptunes and mini-Neptunes have been found orbiting close to their stars, and many show similarly featureless spectra that had puzzled astronomers. LTT 9779b provides the Rosetta Stone. These worlds may host the same reflective mineral cloud decks, protecting their atmospheres from the stellar radiation that should destroy them. The hot Neptune desert might not be as empty as we thought. It's just populated by planets wearing armor made of vaporized stone. The ultra-short period orbit, LTT, 9,779b tears around its star in just 19 hours, placing it among the fastest orbiting planets ever discovered. This ultra-short period means the planet completes nearly 460 orbits in the time Earth makes one trip around the Sunday. To maintain such a frenetic pace, the planet must be extremely close to its star, only 0.017 astronomical units, or about 2.5 million kilometers. For perspective, that's less than 4 stellar radii away from the star's surface. If LTT 9,779b orbited our Sun at that distance, it would be skimming through the Sun's corona. Orbiting at this proximity has profound consequences for the planet's physical state. The gravitational interaction between planet and star generates massive tidal forces. These forces work to synchronize the planet's rotation with its orbit, a process called tidal locking. LTT 9,779b is almost certainly tidally locked, meaning one hemisphere perpetually faces the star while the other remains in eternal darkness. The day side endures continuous roasting under stellar radiation that never sets, while the night side experiences permanent night where temperatures plummet relative to the scorched sunward face. This tidal locking creates the most extreme temperature gradient in the known universe between a planet's day and night sides. Webb's thermal emission measurements indicate dayside temperatures around 2000 Kelvin, while climate models suggest the night side could cool to as low as 800 to 1000 Kelvin, still hot by Earth standards, but nearly 1,200 degrees cooler than the opposite hemisphere. Such a temperature differential drives ferocious atmospheric dynamics. Winds exceeding several kilometers per second howl from the hot day side toward the cooler night side, redistributing heat and transporting vaporized minerals across the terminator. The tidal forces don't just lock the planet's rotation, they also deform its shape. LTT 9,779b is stretched along the axis pointing toward its star, bulging outward in an ellipsoidal shape, rather than remaining spherical. The magnitude of this deformation depends on the planet's internal structure and composition. If the interior has a significant molten component, a magma ocean beneath the atmosphere, the tidal bulge would be more pronounced, with the star's gravity continuously kneading the interior and generating substantial tidal heating. This internal heat source could supplement the external radiation in maintaining high atmospheric temperatures and might contribute to the ongoing outgassing that replenishes the atmosphere. The ultra-short orbital period also means LTT 9,779b experiences extreme tidal evolution. Over time, tidal interactions transfer angular momentum between the planet's orbit and the star's rotation. For a planet this close, the expected outcome depends on whether the planet orbits faster or slower than the star spins. Measurements of LTT 9779 indicate it rotates relatively slowly compared to the planet's orbit. This configuration means tidal forces should gradually drain angular momentum from the planet, causing its orbit to decay and bringing it even closer to the star over millions of years. Eventually, in the distant future, LTT 9779b may spiral inward until it crosses the Roche, limit the distance at which tidal forces overcome the planet's self-gravity, tearing it apart into a ring of debris that will ultimately fall into the star. Calculating exactly when this will happen requires precise knowledge of the tidal dissipation parameters, which remain uncertain. Current estimates suggest the planet may have anywhere from tens of millions to a few hundred million years before it meets this fate, a short remaining lifetime on cosmic scales, but still long enough for extensive study. The close orbit also subjects LTT 9,779b to a relentless barrage of stellar radiation across the electromagnetic spectrum. The planet receives not just visible light, but intense ultraviolet and X-ray flux capable of ionizing atoms and driving complex photochemistry in the upper atmosphere. Webb's observations reveal that the atmosphere shows signs of heavy ionization, with charged particles creating a planetary ionosphere far more extensive than Earth's. This ionosphere likely interacts with the star's magnetic field, possibly generating aurorae as charged particles spiral along magnetic field lines and slam into the atmosphere, though, at these extreme temperatures, any auroral glow would be swamped by the thermal emission from the hot atmosphere itself. The orbital configuration raises questions about how LTT 9779b arrived in its current position. Planets don't form this close to their stars. At the distance where LTT 9779b orbits, temperatures in the protoplanetary disk would have exceeded 2000 Kelvin, far too hot for gases to condense or solids to exist. The planet must have formed farther out, beyond the ice line where volatile materials could freeze, and then migrated inward through gravitational interactions with the disk or other planets in the system. Two migration mechanisms could explain the inward journey. Type 2 migration occurs when a massive planet opens a gap in the protoplanetary disk and then drifts inward along with the disk material as it accretes onto the star. This process typically brings gas giants to close orbits and is thought to create hot Jupiters. However, LTT 9779b isn't massive enough to have opened a substantial gap, making Type 2 migration less likely. Alternatively, high eccentricity migration involves gravitational interactions with other planets or companion stars that place the planet on a highly elliptical orbit. Tidal interactions with the star then circularize the orbit at a close distance, delivering the planet to its current position. Evidence from Webb's observations may help distinguish between these scenarios. If LTT 9779b migrated early through the disk, it would have done so while still accreting material, potentially acquiring a composition reflecting the cooler outer regions where it formed. If it migrated later through dynamical interactions, it might retain compositional signatures from its original formation zone. The detection of heavy elements and minerals in the atmosphere provides clues their abundances can be compared to models of disk chemistry at different temperatures and locations. The ultra-short orbital period also makes LTT 9779b an exceptional target for atmospheric studies. During each transit, the planet blocks a measurable fraction of the star's light, and Webb can analyze how that light filters through the planet's atmosphere. With 460 transits per year, astronomers can accumulate enormous amounts of data, averaging out noise and detecting subtle spectral features that would be impossible to see in planets with longer periods. This observational advantage has already yielded the most detailed atmospheric spectrum of any hot Neptune, and will continue to refine our understanding as more observations accumulate. Atmospheric composition beyond hydrogen and helium. While hydrogen and helium dominate LTT 9779b's atmosphere by mass, as expected for a Neptune-sized planet, Webb's spectroscopic analysis revealed a rich tapestry of heavier elements and compounds that distinguish this world from the ice giants in our solar system. These trace constituents, though present in relatively small quantities, drive the planet's unique atmospheric chemistry and cloud physics. The most significant discovery was the detection of metal species in gaseous form. Webb's near-infrared spectrograph identified absorption features consistent with neutral and ionized forms of iron, magnesium, and silicon elements that on Earth exist only in solid rocks and minerals, but which vaporize at the extreme temperatures of LTT 9779b's dayside. The presence of gaseous metals has profound implications for atmospheric opacity and chemistry. These atoms and ions absorb light efficiently in specific wavelength ranges, affecting how energy is deposited in different atmospheric layers and influencing the temperature structure. Iron, in particular, plays a complex role. Neutral iron vapor absorbs strongly in the near-infrared, contributing to atmospheric heating and potentially forming metallic clouds at slightly cooler temperatures than the silicate clouds. When iron condenses, it creates dark, absorptive cloud particles rather than reflective ones. Models incorporating both reflective silicate clouds and absorptive iron clouds suggest a stratified cloud structure, with bright mineral clouds dominating the uppermost layers and darker metallic clouds forming below, creating horizontal variations in brightness across the planet's surface. Silicon and magnesium, when present as free atoms, participate in gas phase chemistry that can form simple molecules before condensing into silicate minerals. Silicon monoxide, a molecule consisting of one silicon and one oxygen atom, was tentatively detected in Webb's spectra, This compound forms at high temperatures through reactions between silicon vapor and trace oxygen, and it can act as a seed particle for silicate cloud condensation. Understanding the abundance of CO helps constrain models of cloud formation and the vertical mixing processes that transport material between atmospheric layers, though their spectral signatures were weaker than expected. In cooler atmospheres, these alkali metals produce prominent absorption lines, but at LTT 9779B's temperatures, they appear muted. The leading explanation is that sodium and potassium are being sequestered into clouds, bound up in mineral particles rather than remaining in gaseous form. This sequestration reduces their gas phase abundance, weakening their spectral features and providing additional evidence for the extensive mineral cloud decks. Oxygen-bearing compounds beyond simple oxides were harder to detect. Water vapor, which dominates the atmospheres of cooler Neptune-type planets, was notably absent or present only in trace amounts. The extreme temperatures dissociate water molecules, breaking them apart into hydrogen and oxygen, or incorporating the oxygen into other compounds like silicon monoxide or metal oxides. Carbon-bearing molecules like methane and carbon monoxide, common in Jupiter and Saturn's atmospheres, were also not detected. Either carbon is depleted in LTT 9779B's envelope relative to solar abundances, or the high temperatures chemically process carbon into forms Webb cannot easily observe, such as carbon vapor or exotic carbon-bearing aerosols. The lack of traditional volatiles like water and methane distinguishes LTT 9779B from the ice giants Neptune and Uranus. Those planets formed beyond the ice line where water, ammonia and methane ices were abundant, accreting large quantities of these materials. LTT 9779B, despite forming farther out than its current location, may have originated in a region where ices were less dominant, or may have lost its volatile inventory during migration or through atmospheric escape early in its history. The relative enrichment in refractory elements like silicon, magnesium, and iron suggests the planet's envelope has been processed, either through selective loss of lighter volatiles or through contamination by material from a molten mantle. Webb's observations also constrain the atmosphere's metallicity, the abundance of elements heavier than helium. Metallicity is a key parameter in planet formation theories. High atmospheric metallicity indicates the planet accreted significant solid material, either during formation or through later impacts. LTT 9779B's atmosphere shows elevated metallicity compared to its host star, suggesting substantial enrichment in heavy elements. This enrichment could arise from the dissolution of infalling planetesimals during formation, from ongoing mixing with a molten rocky layer below, or from preferential loss of hydrogen and helium over time, concentrating the heavier elements that remain. The vertical distribution of chemical species provides additional clues to atmospheric dynamics. Spectral features from different molecules and atoms originate at different atmospheric pressures and temperatures, allowing astronomers to probe the vertical temperature-pressure profile. LTT 9779B's spectrum indicates a temperature inversion, a layer where temperature increases with altitude rather than decreasing. This inversion likely results from absorption of stellar radiation by gaseous metals and aerosols in the upper atmosphere. The trapped heat creates a warm stratosphere above a cooler troposphere, analogous to Earth's ozone layer heating the stratosphere, but driven by entirely different chemistry. Chemical models constrained by Webb's observations suggest that the atmosphere undergoes vigorous photochemistry. Ultraviolet photons from the star break apart molecules and ionize atoms, creating reactive radicals and ions that drive complex reaction networks. These reactions can synthesize exotic compounds not present in thermochemical equilibrium molecules that wouldn't form if temperature alone governed the chemistry. Identifying these disequilibrium species requires detailed photochemical modeling and comparison with Webb's spectra, work that is ongoing, as astronomers refine their understanding of high-temperature atmospheric chemistry. The atmospheric composition also bears the signature of the planet's formation history. The ratio of different elements such as carbon to oxygen or silicon to magnesium reflects the mix of materials the planet accreted. By measuring these ratios and comparing them to predictions from planet formation models, astronomers can test ideas about where in the protoplanetary disk LTT 9779b formed and how it evolved. Preliminary analyses suggest the planet's composition is consistent with formation beyond the ice line, followed by inward migration, supporting the dynamical history inferred from its orbital properties. The albedo anomaly. LTT 9779b reflects approximately 80% of the light that strikes it, making it the most reflective planet ever discovered orbiting another star. This extreme albedo, formerly measured at 0.8 plus or minus 0.03, places the planet among the most reflective objects in the cosmos, rivaling only Saturn's icy moon Enceladus in our own solar system. Understanding why LTT 9779b shines so brightly has become central to explaining its survival and atmospheric structure. Albedo, the fraction of incident light a surface or atmosphere reflects, depends on composition, particle size distribution, and cloud coverage. Earth's average albedo is about 0.3, meaning it reflects 30% of sunlight and absorbs 70%. Venus, shrouded in thick sulfuric acid clouds, boasts an albedo of 0.75. Gas giants like Jupiter and Saturn have albedos around 0.5, reflecting sunlight off their ammonia and methane cloud layers. LTT 9779b's albedo exceeds all of these, requiring an explanation beyond conventional cloud physics. The silicate clouds identified by Webb provide the answer. Silicate minerals have high refractive indices, meaning they bend light strongly at the boundary between the particle and surrounding gas. This property makes them efficient scatterers. When light hits a silicate particle, much of it bounces off rather than being absorbed. When countless billions of these particles form continuous cloud decks covering the planet's dayside, they create a nearly perfect mirror. The clouds are also vertically thick, extending over hundreds of kilometers. Even if some light penetrates the uppermost layer, it encounters additional layers below, each scattering more photons back towards space. The cumulative effect is an atmosphere that returns the vast majority of incident radiation. Particle size plays a critical role in determining albedo. Optimal scattering occurs when particles are comparable in size to the wavelength of light. For visible light, this means particles around 0.5 microns across. Webb's spectral analysis, combined with ground-based photometry, suggests LTT 9779b's cloud particles span a range from submicron aerosols to several micron droplets. This distribution ensures efficient scattering across the visible and near-infrared spectrum, producing the high albedo observed at multiple wavelengths. The extreme reflectivity has thermal consequences. By bouncing back 80% of stellar radiation, the clouds prevent that energy from being absorbed and heating the atmosphere. Simple energy balance calculations show that LTT 9779b's equilibrium temperature, the temperature it would reach balancing absorbed and emitted radiation, is several hundred degrees cooler than if the planet had a low albedo atmosphere. This cooling directly impacts atmospheric escape rates. Lower temperatures mean slower moving particles, fewer molecules exceeding escape velocity, and reduced mass loss. The albedo anomaly is, quite literally, LTT 9779b's lifeline. Comparing LTT 9779b to other exoplanets highlights just how unusual its reflectivity is. Most hot gas giants have albedos below 0.3, often much lower. These dark planets absorb most of the radiation they receive, heating to temperatures where water clouds can't form and only refractory materials remain. Without reflective clouds, they spiral into a positive feedback loop. Absorbed heat vaporizes any potential cloud-forming materials, lowering albedo further and increasing absorption. LTT 9779b has escaped this fate by forming clouds from minerals that remain stable at the high temperatures where lighter materials would vaporize. The planetary energy budget reveals additional insights. LTT 9779b receives approximately 4,200 times the stellar flux Earth gets from the Sunday. If the planet absorbed all this energy, its dayside temperature would exceed 3,000 Kelvin. Instead, by reflecting 80%, only about 840 times, Earth's insolation is absorbed, still enormous. but manageable. The absorbed energy drives atmospheric dynamics, powering the winds that redistribute heat from day to night. The emitted thermal radiation, primarily in the infrared, carries this energy away to space, maintaining a rough equilibrium between absorbed stellar energy and emitted heat. Webb's observations allowed, for the first time, direct measurement of the thermal emission from LTT 9779b's night side. By observing the planet at different phases when the day side faces Earth versus when the night side is visible, astronomers could map how temperature varies across the surface. The data showed that the night side, despite being permanently dark, remained surprisingly hot around 1000 to 1200 Kelvin. This retained heat indicates efficient atmospheric circulation transporting energy from the day side. The high albedo limits energy input on the day side, but the heat that is absorbed gets redistributed globally, preventing extreme temperature contrasts that would create even more violent dynamics. Modelling the radiative transfer through LTT 9779b's atmosphere requires accounting for the wavelength-dependent properties of silicate clouds. At visible wavelengths, the clouds scatter efficiently, producing high albedo. At longer infrared wavelengths, corresponding to the planet's thermal emission, the clouds become more transparent, allowing heat to radiate into space. This wavelength dependence means the clouds simultaneously reflect incoming starlight while permitting outgoing heat to escape an optimal configuration for cooling the atmosphere. The discovery of such a reflective planet has broader implications for exoplanet demographics. Astronomers conduct surveys to measure the brightness of exoplanets at different wavelengths, using these measurements to characterize atmospheres. If a significant population of hot Neptunes sports similar reflective silicate clouds, they will be easier to detect and characterize than previously anticipated. Conversely, the high albedo means these planets appear brighter in reflected light, but may not emit as much thermal radiation as expected, potentially biasing estimates of their temperatures and atmospheric properties if reflectivity isn't accounted for. Thermal emission and energy transport. LTT 9779b doesn't just reflect light, it also glows with its own thermal radiation, shining brightest in the mid and far infrared, where hot objects emit most of their energy. Webb's mid-infrared instrument captured this glow, measuring the heat radiating from the planet's day side and, crucially, from its night side. These thermal emission maps revealed how energy flows through the atmosphere and highlighted the planet's remarkable heat transport efficiency. The dayside emission spectrum peaks around 1.5 microns, corresponding to a brightness temperature of approximately 2000 Kelvin. This measurement confirmed theoretical predictions and matched the temperatures inferred from the planet's albedo and stellar flux. But the night-side measurements surprised researchers. Despite receiving zero direct starlight, the night side radiates at temperatures around 1200 Kelvin, far hotter than expected if the hemisphere were thermally isolated from the day side. The only explanation is that atmospheric winds transport enormous amounts of heat from the sunlit side to the dark side. Theoretical models of atmospheric circulation on tidally locked planets predict strong equatorial jets, high-speed winds flowing from the hot substellar point toward the cooler night side. On LTT 9779b, these jets likely exceed several kilometers per second, driven by the massive pressure and temperature gradients between hemispheres. As air heated on the day side rises and flows toward the terminator, it carries thermal energy with it. Upon crossing into the night side, the air cools and descends, releasing heat through infrared radiation before circulating back toward the day side to complete the cycle. The efficiency of this heat transport depends on several factors, including wind speeds, atmospheric density, and the radiative properties of the atmosphere. Webb's measurements of the night side temperature constrain these parameters. By comparing observed temperatures to predictions from general circulation models, sophisticated computer simulations that solve the equations of fluid dynamics on a rotating sphere, astronomers can test their understanding of exoplanet atmospheres. Early models of LTT 9779b suggest that the atmosphere has relatively low drag, allowing winds to accelerate to high speeds and carry heat efficiently across the terminator. The presence of silicate clouds adds complexity to energy transport. Clouds affect radiative transfer, scattering and absorbing radiation at different wavelengths. On the day side, they reflect incoming starlight, but they also trap some of the thermal radiation emitted from below, creating a greenhouse effect. On the night side, clouds may continue to form if transported air retains enough vaporized silicate. These nightside clouds could trap heat, contributing to the elevated nightside temperatures. However, as air cools and particles rain out, the night side may become partially clear, allowing more efficient radiative cooling. Webb's observations at multiple wavelengths provided clues to the cloud distribution. Different infrared wavelengths probe different atmospheric pressures. By analysing emission at wavelengths where clouds are optically thick versus wavelengths where they're transparent, astronomers constructed a vertical profile of cloud coverage. The data suggests that clouds extend from near the surface up to the mid-atmosphere, with the densest layers concentrated at pressures around 1 millibar, roughly analogous to Earth's stratosphere but far hotter and composed of vaporized minerals. Horizontal variations in cloud coverage also emerged from the observations. As the planet rotates through its orbit, Webb's instruments detect changes in brightness, indicating that some regions are more reflective than others. These variations could result from patchy cloud decks, with clear regions allowing deeper, hotter layers to radiate more strongly. Alternatively, temperature differences between the equator and poles could create latitudinal bands of varying cloud density, similar to Jupiter's belts and zones but driven by different chemistry. The thermal structure also influences atmospheric chemistry. Temperature determines which molecules can exist in gaseous form and which condense. On the day side, high temperatures keep silicates, iron and other refractory materials vaporized. As air flows toward the night side and cools, these materials condense into cloud particles, depleting the gas phase. Chemical models accounting for this day-night circulation predict substantial compositional differences between hemispheres. The day side should be enriched in metal vapors, while the night side atmosphere contains more condensate particles and possibly exhibits different molecular abundances if cooler temperatures allow new compounds to form. Webb's spectroscopic observations during secondary eclipse, when the planet passes behind the star and its dayside emission is blocked, allowed direct measurement of the night-side spectrum. The data showed reduced emission across all wavelengths compared to the dayside, but the spectral shape revealed important details. Certain absorption features, tentatively attributed to cooler silicate vapors, appeared stronger on the night side, consistent with predictions that condensation enriches certain species as temperatures drop. Energy balance calculations using Webb's measurements constrain the planet's bond albedo, the fraction of total incident energy reflected at all wavelengths, not just visible light. LTT 9779 B's bond albedo appears to be around 0.75, slightly lower than the visible albedo due to absorption in the ultraviolet and near-infrared. This distinction is important for accurately modelling the planet's thermal budget and understanding how much energy drives atmospheric dynamics versus being radiated back to space. The thermal emission data also allowed estimation of the planet's internal heat contribution. Young planets retain heat from their formation and emit thermal radiation beyond what they receive from their star. LTT 9779 B, at roughly 2 billion years old, is not particularly young, and models predict minimal internal heat. Webb's measurements confirmed this, showing that the observed emission can be entirely explained by absorbed stellar radiation, plus the small amount of tidal heating generated by the planet's close orbit. The consistency between observed and predicted thermal emission validates our understanding of the planet's age and thermal evolution. Atmospheric dynamics and superrotation. The combination of extreme irradiation and tidal locking drives atmospheric circulation patterns on LTT 9779 B that dwarf even the most violent storms on Earth. Webb's observations, though not directly imaging winds, constrain atmospheric dynamics through thermal maps and spectroscopic features that carry the fingerprints of global-scale motion. On tidally locked planets, atmospheric circulation typically falls into one of two regimes. In the slow rotation regime, dayside heating drives a simple day-to-night overturning flow, with air rising on the dayside, flowing at high altitude toward the night side, descending and returning at lower altitudes. In the fast rotation regime, the planet's spin deflects winds through the Coriolis effect, generating zonal jets' strong east-west currents that circle the planet parallel to the equator. LTT 9779b's 19-hour orbital period, which equals its rotational period due to tidal locking, places it in an intermediate regime where both processes matter. General circulation models of LTT 9779b predict a phenomenon called superrotation, where equatorial winds blow faster than the planet's rotation speed. This occurs when momentum deposited by the day-night circulation gets concentrated into a narrow jet stream that encircles the planet. Observations of Jupiter and Saturn show superrotation in their atmospheres, and models suggest hot Jupiters exhibit extreme superrotation, with wind speeds exceeding several kilometers per second. LTT 9779b, with its intense irradiation and relatively rapid rotation, likely experiences similar dynamics. Evidence for superrotation comes from the thermal phase curve, the variation in thermal emission as the planet orbits its star. If heat were transported slowly, the hottest spot on the planet would coincide with the substellar point, the location directly facing the star. Instead, Webb's observations revealed a hot spot offset, with the peak temperature shifted eastward from the substellar point by several degrees. This offset indicates that the fastest winds blow eastward, carrying heat downstream and displacing the thermal maximum. The magnitude of the offset constrains wind speeds. Theoretical work shows that a larger offset implies faster winds. For LTT 9779b, the observed offset of approximately 10 to 15 degrees corresponds to equatorial wind speeds around 2 to 3 kilometers per second, supersonic velocities where atmospheric pressure is low. These winds transport thermal energy efficiently, explaining the hot night-side temperatures and the relatively uniform brightness observed across the planet's dayside. Vertical wind shear changes in wind speed and direction with altitude adds further complexity. Models predict that winds near the surface flow in different directions than winds aloft. At the surface, friction and drag slow winds, while at high altitudes, the atmosphere flows freely. This vertical structure creates turbulence and mixing, affecting cloud formation and chemical transport. Spectroscopic observations at different wavelengths, which probe different altitudes, can reveal this structure by showing variations in chemical abundances or temperatures that wouldn't occur in a static atmosphere. The interaction between atmospheric dynamics and cloud formation is particularly intricate. Winds transport vaporized silicates from the hot day side into cooler regions where they condense, forming clouds. The spatial distribution of these clouds depends on wind patterns. If winds are strong and well organized, clouds may form in distinct bands or regions, creating longitudinal and latitudinal variations in reflectivity. Webb's photometric observations hint at such variability, with brightness fluctuations suggesting that cloud coverage isn't uniform. Atmospheric waves represent another dynamic feature. Gravity waves, similar to waves on the ocean but propagating vertically through the atmosphere, are excited by convection and flow over topography. Though LTT 9779b has no solid surface topography, temperature variations can create similar effects. These waves transport energy and momentum, influencing the structure of jets and winds. Kelvin waves and Rossby waves, predicted by theory to exist on rotating planets, could modulate temperatures and cloud coverage over time, producing periodic variations that future observations might detect. The day-night temperature gradient drives not only horizontal winds but also vertical convection. On the day side, intense heating creates buoyant plumes of hot gas that rise rapidly through the atmosphere. These convective towers can reach altitudes of hundreds of kilometers, carrying heat upward and mixing chemical species. At the top of the convective zone, the rising air spreads outward and flows toward the night side. This overturning circulation is analogous to Earth's Hadley cells but operates on a global scale rather than being confined to the tropics. Night-side dynamics differ markedly. Without direct stellar heating, the night-side atmosphere cools radiatively, leading to descending motion. However, the heat transported from the day side prevents the night side from becoming truly cold. The balance between advected heat and radiative cooling determines night side temperatures. Models show that if winds are very strong, the night side remains nearly as hot as the day side, with minimal temperature gradient. LTT 9779b's observed night-side temperature of around 1,200 Kelvin, compared to a dayside temperature of 2,000 Kelvin, indicates partial but not complete heat redistribution evidence of moderately strong winds. Magnetic fields could also influence atmospheric dynamics, although their presence on LTT 9779b remains unconfirmed. If the planet possesses a magnetic field generated by a molten metallic core or conducting layers, this field would interact with ionized gas in the upper atmosphere. Charged particles would spiral along magnetic field lines, creating currents and possibly generating aurorae. Magnetic forces could also affect wind patterns, adding an additional layer of complexity to the circulation. Future observations searching for polarization signatures or radio emissions could reveal whether LTT 9779b hosts a magnetic field. The role of tidal heating. Tidal forces from LTT 9779's relentless gravitational pull don't just lock the planet's rotation, they also generate heat deep within its interior. This process, called tidal heating, occurs when gravitational forces deform the planet's shape, creating internal friction as layers slide past one another. The energy dissipated through this friction warms the interior, potentially influencing the planet's structure, atmospheric composition, and long-term evolution. The magnitude of tidal heating depends on several factors: the planet's orbital eccentricity, the distance to the star, and the planet's internal properties, specifically how easily it deforms under gravitational stress. LTT 9779b orbits in a nearly circular path, which minimizes periodic variations in tidal stress. However, even in a circular orbit, tidal forces work against the planet's internal rigidity. If the planet's interior contains partially molten layers, such as a magma ocean beneath the atmospheric envelope, these layers will flow and deform under tidal stress, generating heat. Calculations of tidal heating rates for LTT 9779b suggest modest but non-negligible energy generation, on the order of 10 to the power of 15 watts. For comparison, Earth's total geothermal heat flow is about 4 times 10 to the power of 13 watts, meaning LTT 9779b's tidal heating could be several dozen times greater than Earth's entire internal heat budget. This energy doesn't dramatically affect the planet's surface or atmospheric temperatures. Those are dominated by stellar irradiation, but it influences deeper structures. A likely consequence of sustained tidal heating is the maintenance of a molten magma ocean at the boundary between the planet's rocky core and gaseous envelope. Theoretical models of Neptune-mass planets suggest they can possess such layers if internal temperatures exceed the melting points of rock and ice. Tidal heating would prevent this magma ocean from solidifying over time, keeping it in a perpetually molten state. This has important implications for atmospheric chemistry. A molten layer continuously in contact with the atmosphere can exchange material, supplying vaporized rock to the atmosphere and potentially absorbing gases that dissolve into the magma. This exchange could explain the abundance of heavy elements detected in LTT 9779b's atmosphere. If the magma ocean contains dissolved silicates, iron, and other minerals, convection would transport these materials upward to the interface with the atmosphere, where they vaporize and mix into the gas. This process, called outgassing, would continuously replenish the atmosphere with rocky material, even as some condenses into clouds and rains out. Without such replenishment, the atmosphere might gradually deplete in cloud-forming minerals, altering its reflectivity and thermal properties. Tidal heating also affects the planet's overall energy budget. While stellar irradiation contributes the vast majority of energy input, tidal heating adds a small internal component. This internal heat contributes to the planet's luminosity, the total energy it radiates into space. Webb's thermal emission measurements can, in principle, detect this contribution if tidal heating rates are high enough. Preliminary analyses suggest that the observed emission is consistent with stellar irradiation alone, placing upper limits on tidal heating. These limits help constrain models of the planet's interior structure, ruling out scenarios where extremely vigorous tidal dissipation occurs. The spatial distribution of tidal heating within the planet is non-uniform. Heating is most intense in regions that undergo the greatest deformation, typically near the interface between different structural layers. For LTT 9779b, maximum heating likely occurs at the core mantle boundary and within any molten mantle layer. This concentrated heating could drive convection in the magma ocean, creating upwelling plumes and downwelling currents that mix the interior and transport heat toward the surface. Tidal heating may also influence the planet's long-term orbital evolution. Energy dissipated within the planet is extracted from the orbital motion, gradually reducing the orbital energy and causing the planet to spiral inward toward the star. The timescale for this orbital decay depends on the efficiency of tidal dissipation, parameterized by a quantity called the tidal quality factor. Higher values indicate less efficient dissipation and slower decay. Lower values mean faster decay. Observations of similar planets suggest quality factors ranging from 10 to the power of 4 to 10 to the power of 6, corresponding to orbital decay timescales of tens of millions to hundreds of millions of years. For LTT 9779b, the orbital decay timescale likely exceeds the remaining main sequence lifetime of its star. The star LTT 9779 will evolve into a red giant in approximately 8 billion years, at which point it will expand and likely engulf the planet. Thus, tidal infall into the star is not expected to destroy LTT 9779b before the star's evolution does. Nonetheless, measuring any ongoing orbital decay could provide valuable constraints on tidal dissipation processes, which remain poorly understood for Neptune-mass planets. Comparison to solar system ice giants. LTT 9779b's classification as a hot Neptune invites comparison to the ice giants Neptune and Uranus in our solar system. While all three planets share similar sizes and masses, their environments and atmospheric properties differ so profoundly that they represent fundamentally distinct types of worlds. Neptune and Uranus orbit the Sun at distances of 30 and 19 astronomical units respectively, far beyond the ice line where water, methane, and ammonia freeze. Their atmospheres are cool, with temperatures around 50 to 60 Kelvin near the cloud tops, and they exhibit the blue and blue-green hues characteristic of methane absorption in red wavelengths. The atmospheres are relatively thin compared to the planet's total mass, overlaying deep interiors thought to consist of water-ammonia-methane ices surrounding rocky cores, hence the ice giant designation. LTT 9779b, by contrast, orbits less than a stellar radius from its host star, receiving thousands of times more radiation than Neptune gets from the Sunday. Its atmospheric temperature of 2000 Kelvin vaporizes ices and rocks alike, creating a chemical environment utterly unlike anything in our solar system. While Neptune's clouds consist of methane ice crystals and ammonia ice droplets, LTT 9779b's clouds are molten silicate droplets, materials that exist as solid rock on Earth. The atmospheric composition reflects these differences. Neptune's spectrum shows strong methane absorption bands and traces of hydrogen sulfide, ethane, and other hydrocarbons formed through methane photochemistry. Water vapor exists deep in the atmosphere but is largely condensed into ice clouds. LTT 9779b's spectrum, by contrast, lacks methane entirely. Instead, it displays gaseous metals like iron and magnesium, species that would never exist in vapor form on the cold ice giants. Dynamically, the planets also diverge. Neptune exhibits powerful wind systems, with zonal jets reaching speeds of 600 meters per second, the fastest in the solar system. These winds are driven by internal heat, as Neptune radiates more energy than it receives from the Sun, powered by slow gravitational contraction and possibly residual heat from formation. Uranus, peculiarly, radiates little internal heat and has weaker winds. LTT 9779b's winds, driven by the day-night temperature contrast, likely exceeds several kilometers per second, dwarfing Neptune's already impressive circulation. The internal structures also differ substantially. Neptune and Uranus are thought to have relatively small rocky cores, perhaps 10 to 15 Earth masses, surrounded by thick mantles of high-pressure ices in exotic states, superionic water, where oxygen atoms form a solid lattice while hydrogen ions flow freely. Their hydrogen-helium envelopes contribute only 10 to 20% of the total mass. LTT 9779b's interior remains uncertain, but models suggest a larger rocky core, possibly 20 Earth masses, overlaid by a thinner envelope proportionally richer in hydrogen and helium. Tidal heating and high temperatures may prevent ice formation entirely, replacing the ice mantle with a magma ocean. Magnetic fields present another contrast. Neptune and Uranus both generate strong magnetic fields, but their field geometries are bizarre, tilted, and offset from the planet's rotation axes, suggesting they're generated in the ice mantle rather than a metallic core. LTT 9779b's magnetic field, if present, would likely originate in a molten metallic core conducting currents through convection. Detecting such a field would require radio observations searching for emissions from the planet's magnetosphere, observations that have not yet been conducted. The comparison extends to atmospheric escape. Neptune and Uranus retain their atmospheres easily. Their cool temperatures and strong gravity keep even light gases like hydrogen bound indefinitely. LTT 9779b, heated to extreme temperatures, exists on the edge of catastrophic atmospheric loss, saved only by its reflective cloud shield. Over its lifetime, it may have lost a significant fraction of its original envelope, whereas Neptune and Uranus have retained nearly all of theirs. Despite these differences, LTT 9779b shares with Neptune and Uranus the distinction of being intermediate mass planets larger than super-Earths but smaller than gas giants. This intermediate class appears to be the most common in the galaxy, with surveys finding that Neptune-sized planets outnumber both smaller rocky planets and larger Jupiters. Yet their diversity is astonishing. From icy worlds at 50 Kelvin to roasted giants at 2000 Kelvin, from clear hydrogen atmospheres to reflective mineral clouds, Neptune-class planets occupy an enormous range of parameter space. LTT 9779b represents an extreme endpoint of this spectrum, a world where the familiar composition and structure of ice giants have been transformed by stellar heat into something entirely new. Migration history and formation scenarios. LTT 9779b couldn't have formed where it currently resides. At 0.017 astronomical units from its star, the temperatures in the protoplanetary disk would have exceeded 2000 Kelvin, far too hot for any solids to condense or gases to accrete. The planet must have originated farther out, in the cooler regions of the disk, and subsequently migrated inward. Unraveling this migration history is key to understanding not just LTT 9779b, but the broader population of close-orbiting giant planets. Planet formation theories generally agree that Neptune-mass planets form beyond the ice line, the distance from a star where temperatures drop below the freezing point of water, roughly 3 to 5 astronomical units in a solar-type system. Beyond this line, water ice and other volatiles freeze onto dust grains, increasing the solid material available for building planets. A solid core can rapidly accumulate mass, growing to several Earth masses. Once the core reaches a critical threshold around 10 Earth masses, it begins capturing hydrogen and helium from the disk, building a gaseous envelope. For LTT 9779b, this formation scenario would place its birth somewhere in the outer disk, possibly 5 to 30 astronomical units from the star. But at some point, gravitational interactions set the planet on a path toward its current close orbit. Two primary mechanisms can drive such migration: disk-driven migration and dynamical scattering. Disk-driven migration occurs while the protoplanetary disk is still present during the first few million years of the system's life. As a planet orbits within the disk, it gravitationally interacts with the surrounding gas. These interactions create density waves, spiral patterns in the disk that exert torques on the planet. Depending on the planet's mass and the disk properties, these torques can cause the planet to drift inward or outward. For intermediate mass planets like LTT 9779b, the typical outcome is inward migration, with the planet spiraling toward the star over timescales of hundreds of thousands to millions of years. However, disk migration usually stalls before planets reach extremely close orbits. The inner edge of the protoplanetary disk, where gas is too hot to remain in vapor form, acts as a barrier. Planets that migrate through the disk typically halt at distances around 0.05 to 0.1, astronomical units still close, but not as extreme as LTT 9779b's orbit. This suggests that disk migration alone may not fully explain the planet's current location. Dynamical scattering offers an alternative pathway. In multi-planet systems, gravitational interactions between planets can become unstable, leading to close encounters that fling planets onto highly elliptical orbits. If a planet is scattered onto an orbit that brings it very close to the star at perihelion, tidal forces from the star can dissipate orbital energy, gradually circularizing the orbit at the close-in distance. This high eccentricity migration can deliver planets to ultra-short period orbits like LTT 9779b's. Evidence for or against these mechanisms comes from the system architecture. If LTT 9779b formed through disk migration, other planets might remain in outer orbits, undisturbed. If dynamical scattering occurred, the system might contain fewer planets, or those that remain might have eccentric orbits. Unfortunately, detecting additional planets in the LTT 9779 system is challenging. Inner planets would be difficult to see due to the brightness of the star and the dominance of LTT 9779b's signal. Outer planets would require long-term radial velocity monitoring or direct imaging, neither of which has been conducted extensively. Chemical composition provides additional clues. Planets that form far from the star in ice-rich regions should accrete substantial water and other volatiles. If LTT 9779b formed beyond the ice line, its interior might originally have contained large amounts of water ice, which would vaporize after migrating inward. The lack of water vapor in the current atmosphere suggests either that the planet formed in a region depleted in water, or that the original water envelope was lost through atmospheric escape or chemical processing. Alternatively, LTT 9779b could have formed closer to the star than typical ice giants, in a region where silicates and metals were abundant but ices were scarce. This would explain the enrichment in refractory elements and the absence of volatiles. However, forming such a massive planet close to the star is difficult without substantial solid material, which is less abundant in the inner disk. Isotopic ratios could help distinguish formation scenarios. Different regions of the protoplanetary disk have different isotopic compositions, ratios of deuterium to hydrogen or oxygen, 1:8 to oxygen, 1:6, vary with temperature and distance from the star. Measuring these ratios in LTT 9779b's atmosphere would reveal the temperature and location of the material the planet accreted, constraining where it formed. Webb spectrographs have the sensitivity to detect isotopic features, though such measurements require extremely high signal-to-noise data and have not yet been reported. The timing of migration also matters. If the planet migrated early, while the disk was still present, it would have interacted with gas and dust, possibly accreting additional material during migration. Late migration, occurring after the disk dispersed, would involve purely gravitational interactions with other planets or passing stars. The planet's atmospheric composition might reflect this timing, with early migrants showing compositional gradients or unusual enrichment patterns from accreting disk material. LTT 9779b's survival in the hot Neptune desert suggests a particular formation or migration pathway that preserved its atmosphere. One hypothesis is that the planet formed with an exceptionally thick envelope, starting with significantly more mass than it currently has. Even after billions of years of atmospheric loss, enough remains to give the planet its current appearance. Calculations show that a planet that began with twice its current atmospheric mass could lose half over 2 billion years and still retain a Neptune-like envelope, especially if protected by high albedo. The question of habitability in extreme environments. LTT 9779b is about as hostile to life as a planet can be. Surface temperatures exceed those of molten lava. The atmosphere rains vaporized rock, and ultraviolet radiation bombards the dayside with intensity thousands of times greater than Earth experiences. No conceivable biochemistry could function under these conditions. Yet studying this extreme world informs the search for habitability elsewhere by defining the boundaries of where planets can survive and how atmospheres respond to intense stellar environments. Understanding atmospheric retention mechanisms is directly relevant to habitability. Planets in habitable zones around smaller, cooler stars M dwarfs face challenges similar to those confronting LTT 9779b, albeit less extreme. M dwarfs emit significant ultraviolet and X-ray radiation, especially when young, which can erode atmospheres through photoevaporation. If planets around M dwarfs can retain thick atmospheres despite this radiation, they might remain habitable. LTT 9779b demonstrates that high albedo and thick cloud cover can dramatically reduce atmospheric loss, a lesson applicable to potentially habitable worlds. The role of clouds in climate regulation also extends to habitability. On Earth, clouds reflect sunlight, cooling the surface. On Venus, thick sulfuric acid clouds trap heat, creating a runaway greenhouse effect. LTT 9779b shows an extreme version of reflective cloud feedback, where silicate clouds keep the planet cooler than it would otherwise be. For rocky planets in habitable zones, understanding cloud microphysics and radiative properties is essential for predicting surface conditions. LTT 9779b serves as a laboratory for testing cloud models under extreme conditions, validating the physics that must be applied to cooler, potentially habitable worlds. The study of atmospheric chemistry on LTT 9779b also advances techniques used in the search for biosignatures. Webb's ability to detect trace gases in a challenging environment, high temperatures, strong stellar contamination, demonstrates the capability to identify atmospheric constituents on smaller, cooler planets. Techniques refined on hot giants like LTT 9779b will be applied to rocky exoplanets, searching for oxygen, methane, and other potential signs of life. Moreover, LTT 9779b challenges assumptions about planet habitability over cosmic time. Habitable zones shift as stars evolve. When the Sun becomes a red giant, Earth's habitable zone will move outward, and worlds that are currently frozen might warm into habitability. Conversely, planets currently in habitable zones will become uninhabitable as their stars age. LTT 9779b's survival for 2 billion years in extreme conditions suggests that planets can endure environmental changes longer than simple models predict, provided they have mechanisms like reflective clouds to mitigate heat. Statistical significance in the exoplanet population. LTT 9779b is not unique merely because it's strange. It's significant because it challenges the observed demographics of exoplanets. The hot Neptune desert is a well-established feature in exoplanet statistics, with surveys like Kepler and TESS revealing a pronounced deficit of Neptune-sized planets in ultra-short period orbits. LTT 9779b is one of only a handful of planets found in this desert, making it a critical data point for understanding why the desert exists and what conditions allow planets to survive there. Statistical analyses of the Kepler planet catalogue show that hot Jupiter's planets larger than Neptune readily exist in close orbits, as do super-Earths and mini-Neptunes with radii below 3 Earth radii. But planets with radii between 3 and 5 Earth radii are exceedingly rare at orbital periods shorter than about 10 days. This gap isn't an artifact of detection bias. Transit surveys are quite capable of finding such planets if they exist. The rarity is real and requires explanation. Photoevaporation theory predicted the desert before it was fully observed. Early models in the 2000s showed that Neptune-mass planets couldn't retain hydrogen-helium atmospheres in close orbits. When surveys began confirming the desert's existence, it seemed like a triumph of theory, but LTT 9779b and a few others such as LTT 9779b and TOI 849b complicate this narrative. Their existence shows that the desert isn't absolute. Some Neptune-sized planets survive. Understanding what makes these survivors special is essential for refining atmospheric evolution models. One possibility is that LTT 9779b is a temporary resident. Perhaps it's in the process of losing its atmosphere and will eventually become a bare rocky core, joining the population of super-Earths. Calculations of current mass loss rates, constrained by ultraviolet observations and atmospheric models, could test this hypothesis. If the loss rate is high, the planet might shrink significantly over the next billion years. If it's low, protected by its high albedo, the planet could remain Neptune-sized indefinitely. Alternatively, LTT 9779b might represent a formation pathway that produces unusually robust atmospheres. If certain formation conditions such as high metallicity or specific migration histories create atmospheres resistant to escape, then planets formed under those conditions would populate the desert. Identifying common characteristics among desert survivors could reveal these conditions, guiding formation theories. The statistical analysis extends to comparisons with the broader exoplanet population. How does LTT 9779b's density, albedo, or atmospheric composition compare to other hot Neptunes and Jupiters? Are there correlations? Do high albedo planets systematically survive better, or do high-density planets resist atmospheric loss more effectively? Large exoplanet catalogues allow such comparisons, and LTT 9779b's well-characterized properties make it an anchor point. Webb's characterization of LTT 9779b also sets a benchmark for future observations. As more planets in the desert are discovered and studied, astronomers can assemble a sample large enough for meaningful statistical tests. Do all desert survivors have reflective silicate clouds? Do they all orbit stars of a particular age or metallicity? Such patterns would illuminate the processes governing atmospheric survival. Future observations and unanswered questions. Despite the wealth of data Webb has provided, many questions about LTT 9779b remain unanswered. The planet's interior structure, the details of its atmospheric circulation, and the long-term evolution of its orbit and atmosphere are all areas ripe for further investigation. Planned observations with Webb and other facilities will continue to refine our understanding and may reveal entirely new surprises. One priority is obtaining higher signal-to-noise spectra to detect trace atmospheric constituents. Molecules like silicon monoxide, titanium oxide, and magnesium hydride could exist in small quantities, providing additional constraints on atmospheric chemistry and temperature structure. Detecting isotopic ratios such as deuterium to hydrogen or carbon, 1,3 to carbon, 1,2, would offer clues about the planet's formation environment and history of atmospheric loss. Time series observations could reveal atmospheric variability. Does the cloud coverage change over time? Are there storm systems or large-scale atmospheric waves that modulate brightness? Webb's ability to observe the planet repeatedly over its 19-hour orbit allows construction of detailed phase curves, showing how thermal emission and reflected light vary with orbital position. Deviations from smooth curves would indicate spatial inhomogeneities, localized bright or dark regions moving across the planet's surface. Observing the planet in additional wavelengths would provide complementary information. Ultraviolet observations with the Hubble Space Telescope could detect escaping hydrogen and measure the current mass loss rate. X-ray observations might reveal interactions between the planet's atmosphere and the stellar wind, or detect auroral emissions if the planet has a magnetic field. Radio telescopes could search for synchrotron emission from trapped charged particles, another signature of a magnetosphere. Long-term monitoring of the planet's orbit could detect tidal decay or perturbations from unseen companion planets. Precise transit timing measurements, accumulated over years, are sensitive to orbital changes on timescales of decades. Discovering additional planets in the system would provide crucial context for understanding LTT 9779b's formation and migration history. Comparative studies with other hot Neptunes will place LTT 9779b in broader context. Planets like HATP26b, GJ436b, and the recently discovered TOI 849b each offer different pieces of the puzzle. Some have clear atmospheres, others show evidence of clouds, some orbit actively flaring stars, others quieter hosts. By studying the full ensemble, astronomers can identify which characteristics are common and which are unique, separating universal principles from idiosyncratic details. Theoretical work will continue to advance alongside observations. Improved general circulation models incorporating the complex radiative effects of silicate clouds will predict atmospheric structures and dynamics with greater fidelity. Coupled interior atmosphere models that account for tidal heating and magma ocean outgassing will link the planet's deep interior to its observable properties. These models generate testable predictions that observations can confirm or refute, driving an iterative process of discovery. Perhaps the most exciting prospect is the search for similar planets around other stars. LTT 9779b was initially identified as a candidate by TESS, then confirmed and characterized through extensive follow-up. TESS continues to survey the sky, and future missions like Plato will extend this work, discovering more planets in the hot Neptune desert. Each new discovery will test whether LTT 9779b's properties are typical or exceptional, building a statistical sample that reveals the true nature of these rare worlds. Implications for planetary science. The discovery and characterization of LTT 9779b reverberate through multiple areas of planetary science, challenging assumptions and opening new avenues of inquiry. The planet defies simple categorization, sitting at the intersection of atmospheres, interiors, dynamics, and evolution. Its very existence forces a re-examination of theories that seemed settled. First, it demonstrates that planets can survive in environments previously thought uninhabitable for gas-rich worlds. The hot Neptune desert is not absolute, and the mechanisms of atmospheric retention are more nuanced than early models suggested. Reflective clouds, in particular, emerge as a critical factor. This has implications beyond exoplanets. It informs our understanding of how planetary atmospheres respond to extreme forcing, relevant to early Earth when solar radiation was different, or to future scenarios as the Sun evolves. Second, LTT 9779b highlights the importance of atmospheric composition in determining planetary fate. The presence of heavy elements and cloud-forming minerals isn't just a curiosity, it's the reason the planet still exists. This underscores the need to characterize atmospheric chemistry precisely, not just for hot Neptunes but for all exoplanets. Small differences in composition can lead to vastly different evolutionary outcomes. Third, the planet illustrates the power of space-based infrared observations. Ground-based telescopes, limited by Earth's atmosphere, cannot access the wavelengths where LTT 9779b's atmosphere shines most clearly. Webb's capabilities have proven transformative, and they foreshadow what future missions will achieve. The James Webb Space Telescope is revealing exoplanet atmospheres with a clarity previously unimaginable, and LTT 9779b is among the first to be dissected in such detail. Fourth, LTT 9779b serves as a reminder of nature's creativity. Planets aren't confined to the types we see in our solar system. From lava worlds to ice giants, from super-Earths to hot Jupiters, the exoplanet zoo contains an astonishing variety. LTT 9779b, with its clouds of vaporized rock and atmosphere hotter than many stars' surfaces, exemplifies this diversity. It reminds us that the universe is not constrained by our expectations. The planet also has broader cultural and philosophical implications. Humanity has gazed at the stars for millennia, imagining other worlds. The discovery that planets like LTT 9779b exist impossible by the standards of mid-20th century science expands our cosmic perspective. It teaches humility. The universe is stranger and richer than we imagined, and it inspires curiosity. If such a planet can exist, what else awaits discovery? LTT 9779b will remain a focus of study for years to come. Each observation adds a piece to the puzzle, revealing the intricate physics governing extreme planetary environments. The planet is more than an outlier or an anomaly. It is a key that unlocks understanding, a natural laboratory where processes invisible in our solar system play out in full view. In studying this impossible world, we learn not just about one planet, but about the principles that shape all planets, everywhere. The discoveries continue. Each transit, each spectrum, each observation brings new data. And with each new piece of information, our picture of LTT 9779b sharpens. The planet that shouldn't exist is teaching us why it does, and in doing so, it's rewriting the rules of planetary science. This is the frontier of knowledge, where the impossible becomes real, and where the universe reveals its deepest secrets to those patient enough to listen.